of all, we learned this one, that it is okay. Right here you see that about thermodynamics. In the previous class, we have discussed three laws of thermodynamics. One is zeroth law, one is first of thermodynamics, and second is second of thermodynamics. And now today I'm discussed with Carnot engine. In the previous thermodynamics, in the previous one, we have already discussed three things. One is zeroth law of thermodynamics, zeroth law, and it is about equilibrium. Zeroth law of thermodynamics, law of thermodynamics, zeroth law of thermodynamics, and the second one is about first law of thermodynamics, first law of thermodynamics, first law of thermodynamics, first of thermodynamics, and the second one is that of second of thermodynamics, second law of thermodynamics. And you know that in second law of thermodynamics, we deal with two things. One is Carnot engine or Henry engine, we say, or another thing that is refrigerator. And we have also learned the various statement of Clausius and Kelvin, that is Stewart statement, Kelvin Planck statement, and Clausius statement. Today, learn about Carnot cycle. In Carnot cycle, you have found this type of graph, and in this graph, you'll find that there are four types of work you have to find out. And in the previous class, we have also learned how the different works we have defined in that. This is a type of work, and here there are three things. One is zero, this is the volume axis, and this is pressure, that is the pressure axis, right? And in pressure and volume axis, we have four equations, four state. One is this one, number one. Number two is in this way. Number three in this way, parallel to this one. And number four is like this. And if you know what it says, actually this type of four, this is Carnot cycle. This one is state. This state is this was P1, V1, this is P1, V1, and temperature is T1, and this point is P2, and the direction is from here to here, the volume increases. You see, this volume is increasing here, again, volume is increasing here, volume decreasing here, volume is decreasing here, right? These two are increasing and these two are decreasing. For P1, V1, T1, and the volume is, this is, the thing, pressure is changing, it is P2, volume is also changing, V2, and this is T1. There is no change in temperature. That means this is isothermal expansion. This is the first one, what we call it as isothermal expansion. This is isothermal. Why isothermal? Because it is same temperature, no change. This is T1, this is also T1. So it is isothermal expansion. Isothermal expansion. And at this point, we have three states, that is P3, the state T3 is P3, this is P3, P3, and T2. There is change in temperature. There is a change in temperature, right? So this we call it as adiabatic expansion. This is adiabatic expansion, adiabatic expansion, adiabatic expansion. What is the meaning of adiabatic expansion? Adiabatic expansion means there is no change of heat. Del Q is equal to 0. You know this one. And isothermal expansion means what? There is no change in temperature. That is del T is equal to 0. You know this one, del T equal to 0. So in this case, it is isothermal expansion. In this case, it is adiabatic expansion. And 3 to 4, it is isothermal compression. You see the volume is decreasing. So here in this case, we'll go at another volume, that is P4. P4, V4, temperature will be same because it is isothermal. So this is known as, this is in this direction, it is in this direction, it is isothermal compression. This is known as isothermal compression. 3 to 4 is isothermal. This part is isothermal compression. Compression means volume is decreasing. And here also see the volume is increasing again. So in this case, the volume is also again decreasing. Therefore, it is adiabatic compression. This one, this part, this direction is adiabatic compression. Adiabatic compression. Adiabatic compression. Now we learn the various types of work done. Again, I am telling you the various types of work done. After that, we learn these types of processes. So first one, you have to remember those things. And just I am repeating once again. The first one is isothermal. Here is the isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. You see, adiabatic compression, there is change in temperature, there is change in volume, is change in pressure. In isothermal expansion, there is change in pressure, change in volume, but not change in temperature. This is T1, this is also T1. This is adiabatic expansion. Here also say pressure is different, volume is different, and temperature is also different, right? And here you can also say P4, V4, T4. That means here you can see at this point, in this point, pressure is different, volume is different, but temperature is same. That means it is isothermal. Isothermal same temperature. So there are four operations. This process, stage 1 to 2, it is isothermal expansion. 2 to 3, adiabatic expansion. 3 to 4, 3 to 4 is isothermal compression, and 4 to 1 is adiabatic compression. So there are four processes, and we are getting four processes in this way. So this is cyclic process. And in cyclic process, you have to learn this is what we call it as Carnot engine. This is known as Carnot engine. This is known as Carnot engine. And today we'll discuss how this Carnot engine work. Before that, I'm going to first learn what are the different types of work done that you have to define. First one is isothermal process. In the previous class, I also discussed this one. Even then, I'm writing so that you can understand this thing. Isothermal process. In isothermal process, equation state equal to PV equal to mu RT. Mu RT. Mu is constant, R is constant, temperature is constant, therefore PV equal to constant. This equation is state of isothermal process. And what is the work done? Work done, you have to remember. Work done in isothermal process, this is actually mu RT. There are two formulas, mu RT, ln V2 by V1, or is equal to mu RT ln P1 by P2. These two you have to remember. That is W equal to mu RT ln P2 by P1 or equal to mu RT ln P1 by P2. This is the work done in isothermal process. And number two is what? Number two is isobaric process. You also know this. Isobaric process. In isobaric process, the first of all you have to know isobar means constant pressure. This is constant temperature. This is constant temperature. This is constant temperature. And this is constant pressure. This is known as constant pressure. Constant pressure. That is isobaric pressure process. And in isobaric process, the work done will be isobaric process. The work done will be like this. Isobaric process, work done. You know this work. First, you know what is the equational state. Isobaric process, V by T equal to constant. V by T equal to what is why it is constant? Because the formula is V equal to P mu RT. Mu RT. In isobaric process, pressure is constant, right? Therefore, you can write that V by T is equal to mu R by P. So here in this case, you see mu is constant, R is constant, and constant pressure is constant. Therefore, V by T equal to constant. V by T is equal to constant, we can say. V by T is equal to constant. If V by T equal to constant, what we get? Work done. So this is what is this? What law is in isothermal process? This is Boyle's law. I already discussed about it. Boyle's law. This is Boyle's law. And in this case, that is isobaric, it is Charles' law. This is Charles' law. This is Charles' law. And there is third one, that is isoporic process. Isoporic. In isoporic process, you use isoporic process, volume is constant. Isoporic process, volume, constant volume. This is about constant volume, constant volume. So if the volume is constant, what you will get? That important, right? So PV is equal to mu RT, PV is equal to mu RT. So V is constant, so you can write that P by T is equal to mu R by V. So mu is constant, R is constant, V is also constant, therefore P by T equal to constant. And this equation is known as Gay-Lussac's law. Gay-Lussac. We already told in the previous class also, Gay-Lussac's law, right? And the fourth one is adiabatic process. I'm writing here after that because we need two things, only isothermal process and adiabatic process. Number 4 is adiabatic process. In adiabatic process, adiabatic. In adiabatic process, you know that del W is equal to 0. Del Q is equal to 0. Del Q. No exchange of heat energy is there. And in adiabatic process, the work done will be like this. The work done will be in adiabatic process, the work done will be this one. W is equal to remember all the formulas. W is equal to what is that formula? 1 by 1 minus gamma into P2 V2 into P2 V2 minus P1 V1. Or that may be is equal to mu R T1 minus T2 T1 minus T2 by gamma minus 1. These formulas to remember, right? In Carnot cycle, you have to remember this formula 1 and 4. No need of 2 and 4. 3. Why? Because we have only two processes: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So now we'll find the work done, total work done. What are the total work done? That I'm going to discuss with you. So I am this one, we know not needed this one. Only the work done for isothermal and adiabatic process is required. Now you see how we're going to do this cyclic process. And this is cyclic process means what? That we started from this point. This is the origin, and this is origin. This is the yes. This is the origin, and this is the volume, and this is the pressure. This is volume axis, this is pressure, this is origin, and now you see this is 0, 0. Now let's say starting from here, you have to go to A to B, B to C, C to D, D to that is a cyclic process. Now it is coming in the same where we started, we get the same final result is also same, right? So this is cyclic process. And Carnot engine, how to find the Carnot engine, that is very important. But suppose we have a hot reservoir at temperature T1. We call it this is hot reservoir. We call it at hot reservoir and a cold reservoir at temperature T2. There are two things in cyclic. One is hot reservoir, we call it as T1, and there is a cold reservoir, it says at T2. But what is that meaning? Meaning that T1 is greater than T2. T1 is greater than T2. What is the maximum efficiency for the possible heat engine operating between two reservoirs? And what cycle of processes should be adopted to achieve the maximum efficiency? We'll find the efficiency. And in the previous class, I already discussed the efficiency with theta. That I'm going to find what is the efficiency in a Carnot engine. That will today find what is the efficiency or eta, right? So Shadi Carnot, a French engineer, first considered this equation in 1824. Interestingly, Carnot arrived at the correct answer, even though the basic concepts of heat or thermodynamics had yet to be firmly established. So we will find the work done, right? A reversible heat engine operating between two temperatures is called a Carnot cycle. First, you have to know what is Carnot cycle. What is Carnot cycle? In detail, it is given in your book also. You will read this both, then you will better understand. We'll only do the calculation so that you can understand the calculation. We expect the ideal engine operating between two temperatures to be reversible engine. Irreversibility is associated with dissipative effects as remarked in the preceding section and worse efficiency. A process is reversible if it is quasi-static and non-dissipative. I already discussed in the previous class it is a reversible process and irreversible process. We have seen that a process is not quasi-static if it involves finite temperature difference between the system and the reservoir. This implies that in a reversible heat engine operating between two temperatures, heat should be absorbed, that is from hot reservoir isothermally and released to the cold reservoir isothermally. We thus have identified two steps of the reversible heat engine. Now we'll find this first one. That is first one is work done. We'll find this one. A reversible heat engine. What is that Carnot engine? A Carnot engine is defined in this way. Carnot engine. So a reversible heat engine, a reversible heat engine, a reversible heat engine operating between a reversible heat engine operating between a reversible heat engine operating between two temperatures, is called a Carnot engine. That is important. Carnot engine. So what is the definition? A reversible heat engine operating between two temperatures is called Carnot engine. And the first temperature T1 is called the temperature of reservoir, and temperature T2, T2, another temperature, that is the two temperatures you have to remember, right? That is two temperatures. One is for hot reservoir is for T1, and cold reservoir is for T2. So what is Carnot engine? First, the Carnot engine should be reversible, right? A reversible heat engine operating between two temperatures is called a Carnot engine. This is definition of Carnot engine. We have just argued that such an engine must have such an engine must have the following sequence of steps constituting one cycle, constituting one cycle. So remember how to find the work done. That is important here, right? The Carnot cycle shown in figure. Carnot cycle shown in the figure. And this is the figure. See, it's shown in figure. Now we'll find the various work done for this process 1 to 2 and this one, right? Let us find what are the work done. This is 1 to 2. This is one state. This is two state. This is third state. And this is fourth state. Now we'll find the various work done, right? Now you see here how we are finding the work done. That is important. How to find the work done, right? So we have taken the working substance. So we have taken the working substance. We have taken the working substance of the Carnot engine of the Carnot engine to be an ideal gas. What is the meaning of ideal gas? Ideal gas means those gases which follow the equation, this one, PV equal to mu RT, those gases are ideal gases. I already told you in the previous class, right? So what are ideal gases? Those gases which follow this equation, PV equal to mu RT, is known as ideal gas. Now we'll find the various steps. Step 1 to 2. Step 1 to 2. So again, I have to draw the formula and draw the efficiency. Draw this graph. So this is P means pressure. This is B means volume. This is B means volume. And this is pressure means P. And we have 4 steps. This is from step 1, P1 to this one, in this way, and in this way, right? So what we are getting, this one, that is this one is P, this is step 1, this is 2, this is 3, this is 4. And this is what? P1, V1, P1 and V1 and T1. And this is what? P2, V2, T1, P2, V2, T1. This is isothermal expansion. This is isothermal expansion. Isothermal expansion, right? And this is this way. And third one is P3, V3, P3, V3, and T2. There is change in temperature, and this is known as adiabatic expansion. Adiabatic expansion. In adiabatic expansion, what happens? Del Q equal to 0, right? And the third one from V3 to P4, this is state P2, P4. This is P4 pressure will change, V4 volume will change, and T2 there is no change in temperature. So it is known as isothermal compression. This is known as isothermal compression. Why compression? Because there is change, volume change, and volume is less. In this case, 4 to 1, it is known as, you see, this is 2 1, this is adiabatic compression. This is known as adiabatic compression. So there are 4 steps. Adiabatic compression. In which region? In this region, right? And this is a total cycle. Adiabatic compression from 4 to 1 adiabatic pressure. Now we'll find the various work done. How to find the work done, that is important for us. Number step 1 to 2, that is isothermal expansion. This is isothermal expansion. Isothermal expansion of the gas. Isothermal expansion of the gas. Isothermal expansion of the gas. Taking its state, taking its state from P1, B1, T1, from P1, B1, T1 to P2, P2, T2, right? So how to find? We have to find the work done. So the heat absorbed by the gas, and which type of gas it is? It is ideal gas. Ideal gas means what? Those gases which follows this formula, we be able to mu R. What is P? Pressure. What is B? Volume. What is mu? Mole. What is R? Universal gas constant. What is T? This is temperature. So step isothermal expansion of the gas taking state from P1, T1 to P2, T2. The heat absorbed. The heat absorbed by the gas, that is Q1 from the reservoir, at temperature T1, is given by this equation. Which equation? So this is also the work done. This is also the work done. From where to what? Work done between 1 to 2. That is this from here to here. Right? This is the work done. We'll find the work done. The work done from 1 to state 2. 1 state to 2 state by the gas on the environment, by the gas on the environment, on the environment, on the environment. What is the meaning? Meaning is that whenever you write by the gas, that means work done will be positive. Work done will be positive. So you can write W 1 to 2. 1 to 2 means what? From here to here. This is isothermal compression. So we isothermal compression, you know that in isothermal the work done, what is the written? Written in this way. The formula for work done is mu r T ln V2 by V1, V2 by V1. So to put this formula here, right? The work done will be this one is equal to Q1, and that will be equal to this one mu r T1, mu r T1, because you have taken this as temperature T1. So mu r T1 ln V2 by V1. This is equation 1. Equation 1. You have to remember, this is isothermal process, so this formula you have to remember. Now step 2, adiabatic expression. Number B is adiabatic. Step 2 to 3. This is step 2 to 3. 2 to 3 means here. 2 to 3, adiabatic expansion, right? Adiabatic expansion of the gas, adiabatic expansion, adiabatic expansion of the gas, adiabatic expansion of the gas from P2 adiabatic expansion of the gas from P2 P2 T1, from P2 expansion from this one P2 V2 T1 to third state, that is P3 V3 P2, this state here to 2 to 3, right? So this one, so work done by the gas using this, work done by the, therefore work done by the gas, work done by the gas, work done by the gas, work done by the gas will be W 2 to 3, 2 to 3. What is the work done? I already told you work done for adiabatic. You see the previous one, what is the work done in adiabatic? You see the formula, this is the formula for adiabatic. You see this one. 1 by gamma minus 1, P2 V2 minus P1 V1, or V1 T1 minus T2 by gamma minus 1, right? So we are writing this equation P mu r T1 minus T2, mu r T1 minus T2 by gamma minus 1, gamma minus 1. This is equation number 2. Equation 2, right? So this is step 1 is this one, 1 to 2. Step 2 to 3, this one, adiabatic expansion. Now we'll find isothermal compression is third one. That is isothermal compression, step 3 to 4. Now we'll get step 3 to 4. Now C is step 3 to 4. 3 to 4. In this step, you'll find that isothermal compression of gas, isothermal compression of the gas, isothermal compression of the gas, isothermal compression of the gas from P3 V3 T2 to P4 V4 T2, right? Now to find the third, that is 3 to 4. So heat released, that is Q, by the gas, by the gas to the reservoir, to the reservoir, to the reservoir, to the reservoir at temperature T2, temperature at temperature T2 is given by the equation, above equation, right? So this is also work done. This is also work done. Work done. That is W 3 to 4 work done on the gas by the environment, on the gas by the environment. So environment. Since this is isothermal compression, the work done will be work done W 3 to 4. That is Q2 is equal to mu R T2 ln V3, mu to R T2 ln V3 by V4. V3 by V4. This is third equation. Equation number 3. We all need all these equations. So this is third equation, isothermal compression, mu R T2 ln V3 by V4. And the fourth step is adiabatic. I already told you that step 4. Step 4 to 1. 4 to 1. This is adiabatic compression. Adiabatic compression. Adiabatic compression of the gas. Adiabatic compression of the gas. Adiabatic compression of the gas from V4 T2 to V1 V1 T1. Adiabatic compression of the gas from P4 T2 to P1 T1. So work done will be work done. Will be how much? Work done will be like this. W 4 to 1. What is the value? The value will be mu R T1 minus T2 T1 minus T2 by gamma minus 1. Now you have to add all the work done. Right? So if you add all the work done, they have 4 work done. This is 1, 2, 3, and this is equation 4. This is equation 4. I have to add all the work done. Now the total work done by the gas in one complete cycle. So we find the total work done in complete one cycle. Total work done. So the total work done by the gas, total work done by the gas in one complete cycle, in one complete cycle. In one complete cycle, what will be the total work done? W is equal to W1 to 2, W1 to 2 plus W 2 to 3 minus W 3 to 4 minus W 4 to 1. Finally, this is the external expansion. This adiabatic expansion, this will be positive. And compression is negative, right? This is isothermal compression, negative work. And this is adiabatic compression, this is also negative work, right? So we add all the 4. So if you add all the 4, you see we W1 to 2, this will cut. That is right. Now we'll find that in equation this one will be equal. Which one? Equation ln B3 by B4. That means equation 4 and equation 2. Equation 2 and equation 4. Equation 2 and equation 4. You see here, equation 2 and equation 4 are equal. Equation 2 and equation 4. What is the equation 4? This is the issue mu r T1 minus T2 by gamma minus 1. Equation 4. And what is equation 2? Equation 2 in the previous case, you see this is same. Equation 2 is this one. Mu r T1 minus. So these are same. So this will cancel. Equation 2 and equation 4 will cancel with each other. Equation 2 and equation, this see here. What is work done? Mu r T1 minus T2 by gamma minus 1, right? Equation 2 and equation 4. Mu r T1, so this one. That is, this will cancel with each other. So we'll get a work done in this value. So 2 will be cancelled and the other things will be total work done will be like this. W1 to 2 plus W 2 to 3 minus W 3 to 4 minus W 4 to 1. So 2 and 4 will cancel with each other. This work done and this work done is same. So one is plus, one is minus, it will be cancelled with each other. So what you're getting, W1 to 2, what we get the value? Mu r T1 ln V2 by V1 ln V2 by V1. Right? And this is minus mu r T2 ln V3 by V4. V3 by V4. So we're getting 1 to 2 and 3 to 4. Right? These equations we got the work done. This one. Now what we find efficiency. Now by definition, the efficiency of eta. I already what we find in concept of efficiency. The efficiency eta of the Carnot engine is of the Carnot engine is the efficiency eta of the Carnot engine is, this is the formula, eta is equal to W by Q. W means what? Work done. Q means what? Heat work. Alright. And this can be defined in this way, 1 minus Q2 by Q1. Q2 by Q1. This is the formula for efficiency of a Carnot engine. Right? I will find this one. This one can be found out by this way. That is 1 minus. It will be found out as 1 minus Q2. Q2 means which one? Q2 means this one. That is this one. T2 by T1. T2 by T1 into ln V3 by V4. V3 by V4 divided by ln V2 by V1. V2 by V1. From where you get, if we put the value of Q2 and Q1, right? Q2 means which one? This is Q2, right? What is that? Mu r T2 ln V3 by V4. So you see here, the mu r will cancel. It is dividing by Q2. Q2 means this one. This is Q2 and this is Q1. So it is this is Q1. So what we are writing? Q2 by Q1. Mu r will cancel, right? Then what you're getting, this is T2 by T1, T2 by T1, right? ln V3 by V4 by ln V2 by V1. Okay. From here we get another thing. It is now since step 2 to 3. 2 to 3 is adiabatic. 2 to 3 is an adiabatic process. Adiabatic process. And you know that in additive process, we have formula P to the gamma equal to constant. You know this one. P to the gamma equal to constant, right? In additive process, P to the gamma equal to constant. So from this relation, we got this value, that is T1 V2 gamma minus 1 is equal to T2 V3 Gamma minus 1. Gamma minus 1. So from here we can write here as V2 by V3 to the power gamma minus 1 is equal to T2 by T1. T2 by T1. You see here, this is V2. We take this V3 downwards, gamma minus 1. So it can be written as V2 by V3. V2 by V3 is equal to T2 divided by T1 into 1 by gamma minus 1. Because this is power. Power means whenever we take this power on the right hand side, it will be 1 by gamma minus 1. Right? So V2 by V3 is T2 by T2, T1, 1 by gamma minus 1. Right? Now also in step 4, similarly, there is a long process you have to remember. Similarly, since step 4 to 1, step 4 to 1 is an adiabatic process, is an adiabatic process. Adiabatic process. So here you can write adiabatic process that T2, same way, same this formula we use. T2 before gamma minus 1 is equal to T1 V1 divided gamma minus 1. From where we got all the relation from this equation. We will PB to the gamma equal to constant. Right? T2 V4 gamma minus 1. So we are getting therefore what are you getting? V1 by V4 is equal to T2 by T1 to the power 1 by gamma minus 1. So you see this equation. This equation and this equation are same. This is suppose A and B. Both are same equation, right? So you see, in place of P2 by P3, you can write T2 by T1, 1 by gamma minus 1. And in place of P1 by P4, T2 by T1, 1 by gamma minus 1, both are same. So you can write V1 by V4 equal to V2 by V3, right? So from equation AB, from equation A and B, from equation A and B, we get, what we get? This equation, that is V3 by V4. That is V1 by V4 is equal to V2 by V3, right? Or you can write another form that V3 by V4, this can be written in this way also. V3 by V4 is equal to V2 by V1. V2 by V1. So this equation is C. Why you taken this one? You see V3 by V4 and V2 by V1, if we cancel, it will be cancel with each other. Right? You see here this equation. V3 by V4 is equal to V2 by V1. That means this will equation cancel. This L and V3 by V4. V3 by V4 equal to V2 by V1. So this one cancel. So you're getting 1 minus T2 by T1. Right? So what you're getting? So we get eta is equal to 1 minus T2 by T1. T2 by T1. This is the Carnot engine. What we found? Carnot engine. What we found? We found in this eta. Eta means what? Efficiency of a Carnot engine. Right? So we have already seen that a Carnot engine is a reversible engine. We have already seen, we have already seen that a Carnot engine is reversible. A Carnot engine is a reversible engine. Carnot engine is a reversible engine. What do you find? That a Carnot engine is a reversible engine, right? So we find this formula, eta equal to 1 minus T2 by T1, right? From here, we can find the various other things also. It is given in your book also. So what we need, you have to prove that eta equal 1 by theta minus. So you have to remember all these 4 points. Or these parts you have to remember. How to find the work done? This eta equal W by Q from a 1 minus Q2 by Q1. And we find this as Q2, this as Q2, this as Q1. Divided by this one. And you see here V3 by V4 is equal to V2 by V1. This will cancel with each other. 1 minus T2 by T1 and T2 by T1 means Q1 by Q2, same thing, right? So we are getting this result. So what is the eta of a Carnot engine? 1 minus T2 by T1, right? So what we get here can be reversed by reversible engine, right? Here we find final remark is what eta is also equal to 1 minus Q2 by Q1. You got it from the definition, right? Q1 Q2. This is this is suppose 5 and this is 6. So we can write from equation 5 and 6, from equation 5 and 6. What we get? We get that Q1 by Q2 is equal to T1 by T2. This equation we got. This is the result of the Carnot engine. So what you have to find? You have to find eta. This is eta is a 1 minus t. This you have to find. So for that you have to write 4 equations. I already told you that this is isothermal expansion, this is adiabatic expansion, isothermal compression, adiabatic compression. There are 4 equations. 1, 2, 3, 4. Right? And this will cancel with each other. This work done, this will be work done will be cancelled because this is compression is negative. This means compression negative. So one will be cancelled, and we get this eta equal 1 minus T2 by 2 at the end. So from inside the book, you follow this Carnot engine and whole derivations are given in your book also. So you have to understand how to remember this formula. This is the eta or efficiency. So there are many other things also that I'm not going to discuss with you. So you get from the book everything, right?
Yes,
And what is this is clearly and what you get, this is clearly against the Kelvin-Planck statement of the second law of thermodynamics. Hence, as this is not needed. Okay, the ideal gas is simple. So we found this as the final remark, right? And is universal relation. This is universal. This Q1 by Q2 by T1 by T2 is a universal relation. Is a universal relation. Is a universal relation. Universal relation independent of the nature, independent of the nature of the system, So we have completed the Carnot engine, whole Carnot engine. What you have to remember? All the work done. What work done? In isothermal process and adiabatic process, and 4 processes you have to remember. From here to here is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, whole engine. And from that, we got this result. Eta equal 1 minus T2 by T1 or eta equal 1 minus Q2 by Q1. From this 5 and 6, you can write Q1 by Q2 is equal to T1 by T2. This is the result, right? Oh, here Q and Q2 are respectively heat absorbed. Here you have to write also here Q1 and Q2, Q1 and Q2 are respectively Q1 Q2 are respectively the heat absorbed heat absorbed and released isothermally released isothermally that is from hot to the cold reservoir, and from the hot to the cold reservoirs, hot to the cold reservoirs, right? In a Carnot engine, in a Carnot engine. Carnot engine in a Carnot engine. Right? So to remember all these things. So therefore, equation 11.2, this equation, this equation can be used, can be used, can be used as a relation, can be used as a relation, can be used as a relation, can be used as a relation to define, can be used as a relation to define a truly universal thermodynamic temperature scale. That is important. Thermodynamic temperature, thermodynamic temperature scale that is independent that is independent of any particular properties of any particular properties of the system used in the Carnot cycle. Used in the Carnot cycle. So you have to revise this Carnot cycle because this is a long process. Of course, for an ideal gas, as a working substance, right? So this universal temperature, this universal temperature, this universal temperature is the same. Universal temperature is the same as the ideal gas temperature, as the ideal gas temperature. So today we have completed this Carnot cycle. This is a long process, so you have to remember all the steps for Carnot cycle. First, what you have to remember, just I'm going to a revision of that. So here you find, this is the finding, you have to find this one first. What is that? That these are the steps of this. These are 4 steps, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. You see, this is isothermal temperature same, P1, P1, T1. Here also you see P2, V2, T1. Why? These isothermal same temperature, right? In this, what is the work done we're getting? Work done is this one, Q1, mu1, T1, ln V2 by V1. And step 2 to 3. 2 to 3 is what? Adiabatic expansion of the gas. That is from P2, V2, T1 to P3, V3, T2. Therefore, the work done by the gas equal to, this is work done by adiabatic. I already told you. This is the work done by adiabatic. You see this one. This is for isothermal. And for adiabatic, mu are T1 minus T2 by gamma minus. We have in the previous class, we have discussed this adiabatic expansion, right? This is the second case. And third case, you see step 3 to 4, again isothermal compression. This one, isothermal compression. That is of the gas from P3, P3, T2 to P4, B4, T2. That is here also 3 to 4, what equate Q2. And that is mu R T2 ln V3 by V4. And here see adiabatic compression. Adiabatic compression is 4 to 1 of the gas. From this one, there is mu R T1 minus T2 by 4 gamma minus 1. So B and C will be cut because this is same. This is same, and this is will be 0. Compression means negative one. Compression means negative one. Expansion means positive one. So this is negative, and that is also negative. So one positive, one negative will be cancelled, and we get only two things, right? That is this one. That is 1 to 2 and 3 to 4. Because these 2, 3 and 4 will be cancelled with each other because they have the same value. If you put the value of W1 to 2, then we are getting mu r T1, T1 ln V2 by V1, and if minus mu r T2 ln V3 by V4, this is Q1, this is Q2. And what is the efficiency? This is the formula for efficiency. The efficiency of eta of a Carnot engine is eta equal to W by Q. 1 minus Q2 by Q1. And what is Q2? This is Q2. What is Q1? This is Q1. So it is T2 by T1. This mu r will be cancelled. Ln V3 by V4 by ln V2 by V1. Similarly, this is step 4 to 1 is the adiabatic process. So T2 V4 gamma minus 1 equal to T1 to 1. From where we get this relation? From this relation Pp to gamma equal to constant. And then it find V1 by V4 by T2 by T1 equal to 1 by gamma minus 1. Here also find T2 by V3 equal to T2 by T1 gamma. So this equation A and B are same, right? So from this equation, we can write V1 by V4 equal to V2 by V3. Or you can write V3 by V4 to V2 by V1. So V3 by V4 and V2 by V1 will cancel with each other, right? So you're getting 1 minus T2 by T1. In the last case, you see, and so we get eta. So this is a long derivation. You have to practice in your copy how it is coming. This is adiabatic isothermal expansion. This is adiabatic expansion. This is isothermal compression. This is adiabatic compression. And two work done will be cancelled, and two work done will be added, and from that I get the value of eta, right? And now you see, we have already seen that a Carnot engine, a reversible engine is this, eta equal 1 minus Q2 by Q1. From this 5 and 6, you can find Q1 by Q2 equal to T1 by T2. This is the universal relation independent of the nature of the system. Here Q1 and Q2 are respectively the heat absorbed and released isothermally from hot reservoir to cold reservoirs in a Carnot engine. This equation can be used in a relation. And total work done by the gas, I already told you this one. And the next thing is this one, that is to define a truly universal thermodynamic temperature scale that is independent of any particular properties of the system used in the Carnot cycle. Now, of course, for an ideal gas, well, as a working substance, so we taken ideal gas as a working substance in Carnot engine. And for this universal temperature is the same as the, so what you have to do in this period, you have to write in your copy about Carnot cycle. This is a long process actually, Carnot engine, right? In Carnot engine, what you have to do? You have to prove that eta is equal to 1 minus T2 by T1. This we have to prove. This proof have to, right? This is the Carnot engine. I already told you in second law of thermodynamics, there are two things. One is heat engine and the refrigerator. And this second law of thermodynamics, so we need second law of thermodynamics to need to explain all the natural phenomena of the universe. And you see here what we get at the end, of course, for an ideal gas as a working substance, universal temperature is the same as the ideal gas temperature, right? That is, what is the thermodynamic scale temperature? It is Kelvin. This one, capital T. So we'll get all these things, Carnot engine also, right? So in this way, what you do at home, first you write all the Carnot engine diagram first you draw. This diagram you first draw, and then find the work done from here to here, then from here to here, then from here to here, then add all the work done. This is W1, this is W2, this is W3, W4. Add all the work done, and 2 will be cut, right? This is W4, 2 will be cut, and 1 will be, and after that, it gets this value, it is 1 by T2 minus T1, and the end, what you will find that Q1 by Q2, Q1 by Q2 is equal to T1 by T2. This is the reference. At the end, we will get this value. And it, okay, and here what we have taken? We have taken an ideal gas. Ideal gas means what? Ideal gas are those equations which follows this relation P equal to mu R T. What is P? What is B? What is mu? Mole. What is R? Universal gas. What is T? Temperature. Temperature. What temperature? It is actually Kelvin temperature, right? The DSI system, not centigrade. It is not centigrade. It is in Kelvin scale. Okay.
Yes,
so we have completed the Carnot engine. You do at home. If there is any problem, then ask me on the next day. Okay.
Okay.
Okay. And when is our next class? On Wednesday, right? Wednesday at 8:30, right? Wednesday at 8:30. So before that, you revise this chapter Carnot engine. Okay. because you have learned the various processes, you learned the isothermal process, adiabatic process, you have learned all these things. So you Carnot engine, you have to revise at home. Okay. Okay. And the next class will be at 8:30. And next on Wednesday, I will do some problems of motion state line. Okay. This one is motion in straight line. We will do also again on that day, motion in straight. Actually, this is a long class. Carnot engine is a very much hectic calculation. So you have finished this motion in straight line. We will do in the next class. Okay. Okay. And at the end of the class, I am sending a payment link. You can tell your father also, right? Okay.
Yes, sir. We will pay
Okay.
tonight.
Okay, no problem. It's okay, no problem. Okay. And so today we are on the next day we'll have meeting at 8:30. Okay.
Yes, sir.
Okay. Thank you.
Thank you.
Okay.
Thank you.